This video will focus on the learning target. I can use a value of Q, which is called the reaction quotient, to predict and also justify whether a reaction will proceed towards the products or towards the reactants as equilibrium is approached. Essentially, Q goes with the Le Chatelier principle in that if I'm given information about the actual amounts of reactant and product when I'm not at equilibrium, I should be able to predict whether the reaction will shift toward reactant or shift toward product based on the value of Q. So Q, again, is called the reaction quotient, and it's capital Q here. And what Q is it's a number that we calculate identically to the way we calculate K, except the numbers we're plugging in to the expression are the numbers when I'm not at equilibrium. So for example, let's say I was at equilibrium and I added a stress. Well, that stress means I'm no longer at equilibrium and the amounts of reactant and product are not the amounts at equilibrium. So if I took their values and plugged it into the essentially the K expression, what I would calculate out is Q. So Q is just the ratio of product to reactant when I am not at equilibrium. And from that information, we'll be able to determine whether the reaction is going to shift toward products or shift towards reactants when we compare it to the K value. So again, if you look at this, this is no different than the math you've done, but the big deal about this is that to get a Q, it's plugging in numbers when you're not yet at equilibrium. So how does the value of Q tell you anything about how the reaction will proceed? Well, if you plug in numbers into that expression when you're not at equilibrium and you get a Q that ends up having a value greater than the K, what that means is as the reaction shifts to get to equilibrium, you're going to essentially have to shift so that that Q lowers. Because when you're at equilibrium, Q is K. Right? If you plug numbers into the expression and what you get out is the value of K, then that means equilibrium. And if you plug in the numbers and you're not at equilibrium, you won't get K. So the way we use Q, again, is we just take numbers of reactant and product not at equilibrium, plug them into our equilibrium expression, and if the value we get out for Q is too big, that means we're going to shift towards the reactants. The reason we shift towards the reactants is to make Q get smaller, we have to increase, essentially, the denominator to bring the value down. Right? So if Q is too big, we will shift to the left and make more reactants. If Q is too small instead, if Q needs to become bigger in order for the equilibrium to be reached, that means we'll shift towards production. So if Q is bigger than K, we're going to shift to the left towards the reactants. And if Q is smaller than K, we're going to shift towards the right, towards the products. That's really it in terms of this concept. What we will do with this is apply it to math. So if you look at this problem, it looks identical to the problems we've had so far. We have an equilibrium expression, we have a K value. The difference is if you read the problem here, it doesn't say that these are the values at equilibrium. It just says, here's what I put in. So if we take these values and plug them into the equilibrium expression, what you're going to get out is not K, you're going to get out Q. And by comparing Q to K, we'll be able to figure out which direction the reaction will proceed. If for number 1 we do a calculation where the value of Q is less than K, then the way the reaction is going to shift is to shift to make the Q value bigger, because you essentially aren't going to get to equilibrium until Q equals K. The way we make Q bigger is we shift toward products. So if we calculate that Q is less than K, then we will be product favored and we'll shift towards the right. If instead we calculate that Q is greater than K, then we're reactant favored and we'll shift towards the left. That's it for this. Have a nice night.